2026 A-Level Physics Paper 1, questions 41 up to 50. If you are interested in a further question from question 1 up to question 40, then check out the links in the description down below. Now moving on to the first question, question 41 says, a uniform steel wire rigidly fixed at both ends is subjected to a tension of 750 newtons. The length of the wire is 0.4 meters and it has a mass of 0.3 grams. Now given this, they ask us, what is the highest harmonic produced by this wire that could be heard by a person who is capable of hearing frequencies up to 10,000 Hz. Now to start with the question, we need to know that the speed of sound in a stretched wire is equal to the square root of tension divided by mass per unit length mu. Alternatively, you could substitute instead of mu, tension divided by mass over length. And rearranging, you can see we will get tension times length divided by mass. So this is the formula for the speed of sound in a stretched wire. Now according to that, for this stretched wire, V is equal to the square root of tension, or 750 newtons, times the length of 0.4 meters divided by the mass, which is 0.3 grams, or converted to SI units, 0.3 times 10 to the minus 3 kilograms, or 3 times 10 to the minus 4 kilograms. So substituting in, we can see we get divided by 3 times 10 to the minus 4 kilograms. So we get this as the answer for the speed of sound in the wire. Now here, since we used SI units, the answer we get is going to be in meters per second. So considering that, we can see if we simplify, we get the square root of 750 times 0.4, which is equal to 300, divided by 3 times 10 to the minus 4, which will give us 100 divided by 10 to the minus 4, which is equal to 100 times 10 to the 4, or 10 to the power of 6. So we get the square root of 10 to the power of 6, which is equal to 10 to the power of 3, or 1000 meters per second. So therefore, the speed of sound in the wire here is equal to 1000 meters per second. Now taking that answer, let's next consider the vibrations that we'll get inside of this wire. So given a stretched wire like this, if we have vibrations inside of the wire, then the first harmonic will be a standing wave with a single antinode in the middle and the two nodes being equal to the two endpoints of the wire. So it will be a standing wave that looks like this. Now considering that, we can see if the length of the wire is 0.4 meters and this standing wave right here has a wavelength which is equal to double of that, since we have only half of the wavelength here, or lambda over 2 over here, we can conclude that lambda over 2 is equal to 0.4 meters, and therefore lambda is equal to 0.4 times 2, or 0.8 meters. So therefore, for this particular vibration, lambda is equal to 0.8 meters. Now to find the frequency of this harmonic here, the first harmonic, which is F1, we can use the formula V equals F lambda. Rearranging, we can see we will get F being equal to V over lambda. Now for the first harmonic F1, the frequency F1 is going to be equal to V or 1000 meter per second divided by lambda, or 0.8 meters, which is equal to 1250 per second, 1250 Hertz. So therefore, the first harmonic F1 has frequency of 1250 Hz. Now any harmonic after that, let's say F sub n, will have a frequency of n times F sub 1. So considering that, we can see for each of these harmonics, F4, F5, F6, F7 and F8, all you have to do to find the corresponding frequency is to simply multiply this fundamental or first harmonic by the corresponding value of n. So therefore F4 will be 4 times F1, F5 will be 5 times F1, F6 will be 6 times F1, and so on and so forth. And the highest one here, F8, will be 8 times F1. Now since they're asking for the highest harmonic, the best way to see which of these will be the highest one that's heard is to start from the highest one, or F8. So the 8th harmonic here will have frequency F8 being equal to 8 times F1, or 8 times 1250 Hz, which is exactly equal to 10,000 Hz. Now here you might have a little doubt, because they say you can hear frequencies up to 10,000 hertz. So does that mean like it's including 10,000 hertz? But in this case, they actually meant including 10,000 hertz. So therefore, if the person can hear up to 10,000 hertz and the 8th harmonic here can actually produce exactly 10,000 hertz, then the person here should be able to hear that harmonic, and therefore the answer is answer number 5, the 8th harmonic. If the first harmonic here is 1250 hertz and the 8th harmonic produces 10,000 hertz and the person can hear 10,000 hertz, then the highest harmonic the person can hear is 10,000 hertz and therefore 8th harmonic. So the answer here is answer number 5, 8th harmonic. Now moving on to the next question, question 42 says, a combined metal rod consists of a gradually decreasing cross-sectional part AB and a gradually increasing cross-sectional part BC as shown in the figure. So in the figure we can see the cross-section decreases from A to B and then increases again from B to C. Now given this, they say the rod is fully lagged, i.e. fully thermally insulated, and the ends of A and C are maintained at temperatures θ1 and θ2 respectively, where θ1 is a higher temperature than θ2. Now given this, they ask us at the steady state, i.e. when the temperatures throughout the rod are all constant, which of the following graphs best represent the variation of the temperature θ of the rod with the distance d along the axis of the rod starting from the point A and going in the direction of the point C. Now for this question, all we need is the single formula dq by dt equals Ka times d theta by dl, where dq by dt is the rate of heat flow per unit time through a given object. K is the coefficient of thermal conductivity of that object, which is constant for that given material. A is the cross-sectional area through which the heat dq is flowing, and finally d theta by dl is the temperature gradient across the area A. Now going up, we can see from θ1 to θ2, as we go along this rod, the temperature should go down. But as it goes down, since this rod is radial symmetrical, across each of these cross sections, the temperature on each of these points here should be equal to a constant value. At these points, it should be equal to a different constant value, and so on and so forth along the length of the rod. So therefore, for each of these cross sections, the temperature gradient at that particular point should be a given value. So at this one it's one value, at the next point is another value, and so on and so forth along the length of the rod. Now considering that, as we go along the rod, if the rod is perfectly lagged, i.e. it's perfectly thermally insulated, no heat can escape out of the rod like this. So therefore, if a certain amount of heat dq by dt enters the rod from the first cross section like this, then through every other cross section, the same amount of heat dq by dt must flow per unit time. So therefore, along the entire length of the rod, for all of these vertical cross sections, dq by dt is a constant. So this value right here is a constant across the entire length of the rod. Now considering that, we can see if that's a constant, we have a constant being equal to k times a times d theta by dl, where k is also constant. Now if we take this equation and convert it into a proportionality, we can see dividing out both of the constants, we get 1 proportional to a times d theta by dl, or conversely if we rearrange this, we can get d theta by dl being proportional to 1 over a, or inversely proportional to a. So therefore, d theta by dl, the temperature gradient across the given cross-sectional area, is going to be inversely proportional to that given cross-sectional area. Now considering that, as we go along the length of the rod, at the starting point, d theta by dl will have a certain value. We'll call it d theta by dl 1. As we go along the rod towards the center, since the cross-sectional area decreases and d theta by dl is inverse proportional to cross-sectional area, as we go towards the center, the value of d theta by dl should increase. So therefore, at the center, if we have, let's say, d theta by dl 2 or something, this d theta by dl 2 will be greater than d theta by dl 1. Now after that, as we move along the tube to the other side, at the very end here, if we have d theta by dl 3, then since this size of the cross-sectional area of this part of the rod is equal to the initial cross-sectional area over here, both of these d theta by dl1 and d theta by dl3 will be equal to each other. So therefore, if we graph d theta by dl, it should increase and then go down again. So from the middle, from the left hand side, if we go towards the middle, it should go up, stop increasing and go down again. So therefore, the temperature gradient from left to right as we go through this rod should increase and go down again. Now, in each of the graphs, what we have is the temperature versus distance. And therefore, the gradient of these lines here is exactly what d theta by dl, the temperature gradient, is representing. So according to that, in each of these lines, we need to see if at the start we have the same gradient as at the end, and in the middle we have a maximum gradient which slowly increases and starts going down again. Now looking at the example graph, we can see in the first graph, our gradient is increasing because it gets steeper. However, after the midpoint of B, the gradient does not go down again. It should be equal to the same gradient that we have over here, but instead it is this gradient right here. So therefore, graph 1 is incorrect. Now looking at graph 2, we can see at the start and at the end, we have approximately the same gradient here. Like if I draw this line, the tangential line like this, and the tangential line here, you can see the two tangential lines are approximately parallel, and therefore they have the same gradient d theta by dl1 and d theta by dl3. So therefore, this part looks correct. Now look at the middle, we can see in the middle the gradient is steeper in the negative direction, as therefore higher than at the two endpoints. And therefore, the gradient increases and then decreases again. So answer 2 is actually the correct answer. Now looking at the other ones, we can see for number 3, we have a decreasing gradient over here. So therefore, it is increasing the downward direction. But there's a weird thing that happens at the center. At the center, to the left of the center, it's one gradient, but to the right, it suddenly changes to a different gradient. So the gradient here suddenly changes. Now, if the gradient suddenly changes, it means that A must also suddenly change. So what this graph is representing is actually a graph that looks like this. We have a decreasing area. The area suddenly changes such that the gradient becomes higher. So if the gradient becomes higher, it means the area suddenly becomes lower, like this. And then because the gradient slowly becomes less and less steep again, it is increasing the cross-sectional area. So therefore, an object that looks like this is correspondent for graph number 3. It is not correspondent for this object right here. So therefore, answer number 3 is wrong. Now moving on to 4 and 5. 4 and 5 are quite easy because in both of them, the gradient is just decreasing all the way through. It's going down, flattening, and over here also it's going down, flattening and flattening. So both of these have decreasing gradients, which would only make sense if the tube was increasing in size only like this. So therefore, all of those are wrong, and the correct answer is answer number 2. Next, if we consider question 43, it says a solid conducting sphere with radius capital R carrying a charge of plus Q is concentric with a very thin insulating shell of radius 2 capital R, which is itself also carrying a charge of plus Q. They then say the charge is distributed uniformly over the surface of the insulating shell, and given this, which of the following graphs best represent the variation of the electrical field intensity E with the radial distance simple r from the common center of the insulating shell and the conducting sphere? So going down, we have a setup that looks like this. We have a central solid sphere, a conducting sphere of radius capital R holding a charge of plus Q on its surface, and concentric to it, we have another spherical shell, an insulating spherical shell of radius 2 capital R, which is itself holding a charge of plus Q on its surface. Now given this, they ask us what is the variation of the electrical field intensity E given by Q divided by 4 pi epsilon r squared, where Q is the amount of charge that is enclosed by a spherical Gaussian surface of radius r that is centered at the same center of the sphere and the concentric spherical shell. Now, to analyze this, let's first consider r's in between 0 and capital R. So for r's in between 0 and capital R, we can see the Gaussian surface we create will be like this on the inside of the solid conducting sphere. Now since on the inside of the sphere we have 0 charges, we can conclude that the charge here inside of the Gaussian surface will also be equal to 0 for all of the radii of simple r in between 0 and capital R. So therefore, in between 0 and capital R, if Q is equal to 0, then the value of E must also be equal to 0. So considering the graph, we can see we must have in between E, or rather R equals 0 and R equals capital R, a value of E equals 0. Now considering the graph, we can see the only graph that doesn't do this is graph number 5. In graph number 5, we have a non-zero value of E in between R equals 0 and R equals capital R. So therefore, graph number 5 is incorrect. Now moving forward, at the point where we break the surface and reach R equals capital R, we are now going to have a charge of plus Q enclosed within the Gaussian surface. So therefore, at this point, at the exact point of R equals capital R, we should have E equals Q divided by 4 pi epsilon capital R squared. Now as we go outward, if we next consider the range from R equals capital R until R equals 2 times capital R on the other surface here, we can see in between those two surfaces, for any Gaussian surface, the charge inside of the surface will be equal to just plus Q. So all the way from R equals capital R to R, we will have only a plus Q on the inside. So along that, until we get to 2R, we should have the same exact variation of the electrical field intensity downward like this until we get to 2R. Now at 2R, we can see just before the 2R, at like a point like this, we'll have R approximately equal to 2R, and we'll still have the same charge of plus Q enclosed within the sphere. So therefore, E will be equal to Q divided by 4 pi epsilon times 2R whole thing squared, which if you simplify will turn into 4 times 4 or 16 times pi, 16 times pi times epsilon times capital R squared. So at this point right here, almost breaking the surface, will be at this value right here of E, which you can see is not equal to 0. However, if you look at the graph, you'll see in this graph and this graph, at R equals 2 capital R, we have 0 intensity, and therefore both of these graphs are incorrect. We cannot have 0 intensity. We should instead have intensity like this, which is approximately equal to 1/4 of the whole intensity at the value of R equals capital R. So we should have a graph like this, meaning that 1 and 3 are still alright. Now after breaking the surface, if we consider a point just outside the surface, we'll have R again approximately equal to 2 capital R, but this time for E, we have the charge of plus Q and the other charge of plus Q both inside of our Gaussian surface. So now, instead of Q on the numerator, we should have Q and another Q or 2Q on the numerator. And therefore, for E, we'll have 2Q divided by 4 pi epsilon times 2R whole thing squared, which we simplify is turning into divided by 16 pi epsilon R squared, and simplifying we can see we get Q divided by 8 pi epsilon R squared. If you cancel the 2, we get Q divided by 8 pi epsilon R squared. So we can see the value of flux here, not flux, value of intensity here is double the intensity that we have just before this point right here. Now furthermore, we can also see it is equal to 1/2 of the initial flux that we had over here. So the flux right after passing 2R must be equal to double of what we had before passing 2R and half of what we had initially. Now going up, looking at the two graphs, we can see in the first graph, this is the initial flux, this is the flux right after 2R, and this is the flux just before 2R, and we can see the flux right after 2R is equal to double of this and half of this, and therefore graph number 1 is correct. Now graph number 3 is incorrect because here the flux that we had before and the flux that we had right after 2R are having a relationship of 2, but we can see the flux after 2R is double instead of half of the flux at R, and therefore it is incorrect. So graph number 3 is incorrect, and the correct answer here is answer number 1. Now moving on to the next question, question 44 says, two square conducting plates with sides of length L are separated by distance D. A dielectric slab with dielectric constant K sides of length L and thickness of D is inserted a distance x into the space between the two plates as shown in the figure. Now given that they ask us what is the effective capacitance of the system. So here what they're asking is what is the effective capacitance between these two plates. Now to ask this, I'm going to consider the parts of the plates that have the dielectric between them as one capacitor and the parts of the plates that have nothing in between them as another capacitor separately. Now considering that we can see the total capacitance is equal to the sum of these two capacitances, as what we have here is two parallel capacitors. So therefore, to find the total capacitance, I just have to find the capacitance of this capacitor and this capacitor separately and then add them together. Now considering this, we can see for the first capacitor, the two plates here both have a height of x, and since we have square plate altogether, the thickness here is going to be L inward. Now therefore, the area of these plates here, A, is equal to L times x. Now considering dielectric here, we can see the actual permittivity here, epsilon, is equal to K times epsilon naught. So therefore, for this capacitor right here, the area of the two parallel plates is equal to Lx, and the permittivity here, epsilon, is equal to K epsilon naught. Now the separation here is equal to D, and considering that for any capacitor, since capacitance is equal to epsilon A over D, for the first capacitor, which I'll call C1, we have K epsilon naught instead of epsilon. Instead of A, we have Lx, and instead of D, we still have D, because here the same variable is D. So we get C1, the capacitance of these two plates right here, being equal to K epsilon naught Lx divided by D. Now for the other part of the plates here, the height of these two plates is equal to the total height L minus the height x. So the height here is L minus x. Now since we have square plates here, the thickness is still L, and therefore the area here is going to be equal to L times L minus x for the second two plates. Now considering that, if we take a look at the epsilon here, since there is nothing in between the two plates, epsilon is going to be equal to epsilon naught. So therefore here we have epsilon naught. Now according to that, we can see if epsilon is equal to epsilon naught and the distance is equal to D, then C2 will be equal to epsilon naught times L minus x divided by D. So this is the value of C2. Now according to that, since we have two parallel capacitors here, the sum of these two capacitances will be equal to the total capacitance of the overall capacitor. And therefore, for the overall two plates here, the capacitance C is equal to C1 plus C2. And we can see, if we substitute, we can see we'll get K times epsilon naught times L times x divided by D plus epsilon naught times L minus x divided by D. Now simplifying, we can see if we take epsilon 0, L and D as constants out of this, we get epsilon 0 times L divided by D times all the stuff on the inside, which is here K times x and over here L minus x. So K times x plus L minus x. So we get this thing right here. Now simplifying, we can see we get epsilon 0 times L divided by D times, if we factorize out the x, we'll get L plus K times, or rather x times K minus 1. And therefore, this is the formula for the capacitance in between these two plates, depending on all of these variables. Now looking at the answers, we can see this answer is there as answer number 1. Epsilon naught L divided by D, epsilon naught L divided by D times L plus K minus 1 times x, L plus x times K minus 1. And therefore the answer here is answer number 1. Now moving on to question 45, it says an infinitely long straight wire carries a constant current I. A rectangular conducting loop starts moving at a constant velocity v as shown in the figure at time t equals 0 while keeping the separation d between itself and the wire a constant. They also say the wire and the loop lie in the same plane. So what's happening here is that this loop moves along the length of the wire like this at the same constant velocity v while keeping the separation between itself and the wire d a constant. Now given this, they ask us which of the following graphs best represent the variation of the current I induced in the loop with time t. Now this question is actually quite easy, and the answer here is answer number 2. To understand why, recall that the EMF generated in a closed loop is equal to negative rate of change of magnetic flux with respect to time. So therefore, if the flux in this thing right here is not changing, then there will be zero EMF and thus zero current. Now considering the loop, we can see, since the loop maintains a constant distance with the wire, along each of these lines, the magnetic flux will have the same constant value. So therefore, the magnetic fields here will have the same constant value along each of these lines that are parallel to the direction of the straight wire. So if the flux here is a certain value, such that the magnetic field here is B1, and here let's say B2, here B3, here B4, and so on, along each of these lines, the amount of flux that passes through this loop here will be constant whether the loop is over here, or literally anywhere else along the wire. No matter where it is, the amount of magnetic flux that goes through this loop will be constant along the entire length all the way up to infinity. Now due to that, the change of magnetic flux with respect to time is equal to 0 divided by a certain amount of time, which is 0, and therefore, since this side is 0, the EMF generated is 0, and therefore the current will also be 0. So the answer here is answer number 2, since the current induced is always 0 with respect to time. So the answer is answer number 2. Now moving on to question 46, it says, when the radius of the soap bubbles increase from R to 2R isothermally by blowing air into the bubble, then the surface area of the bubble increases by E1. It then says, when two identical soap bubbles, each of radius R, made from the same soap solution, coalesce to form a single soap bubble, the surface energy decreases by E2. Given this, they ask us, what is the magnitude of the ratio E1 divided by E2? Now for this question, we know that for a soap bubble of radius R, the surface energy of that bubble is equal to double the surface area, or 8 pi r squared times surface tension T. Now considering that for E1, we initially have a bubble of radius R that's turned into a bubble of radius 2R. So therefore, if you consider initial energy and final energy, initial energy here is 8 pi r squared T, and final energy here is 8 pi 2r squared T. So subtracting these two, E1 must be equal to 8 pi times 2r squared over 4r squared times T minus 8 pi times r squared T. And here we can see, if we take out the 8 pi and T, we get 8 pi T times 4r squared minus r squared, or 3r squared. And therefore we have 8 pi T times 3r squared, or 24 pi r squared T. So therefore E1 is equal to 24 pi r squared T. So that is energy E1. We're going to write that in the corner, and then we'll try to find E2. So E1 is equal to 24 pi r squared T. Now for E2, let's consider coalescing two bubbles. So initially, we have two bubbles, each of radius R, and we combine them to form a single bubble, and here we assume that the volume of the bubble here is equal to the sum of these two volumes. So therefore, if the volumes here are 4 pi by 3 r cubed, then the volume of this one is going to be double of that, or 2 times 4 pi by 3 r cubed. Now according to that, if this is equal to 4 pi by 3 times the actual radius, which I'm going to call capital R cubed, like this, then we can see capital R cubed must be equal to 2 times simple r cubed, and therefore capital R is equal to the cube root of 2 times r cubed, and therefore it's equal to 2 to the power of 1 over 3 times the cube root of r cubed, which is equal to r. So we get this relationship right here. The big radius is equal to cube root of 2 times r. Now from this we can see, if we compare energies, initially the first bubble here has energy of 8 pi r squared T. The second one also has 8 pi r squared T. But for the other bubble, we have 8 pi times 2 to the power of 1 over 3 r squared times t, which if you simplify you can see is going to be equal to 8 pi times 2 to the power of 2 over 3 times r squared t, because if you take 2 to the power of 1 over 3 and take that to the power of 2, you get r to the power or 2 to the power of 2 over 3. So we get this expression right here. Now if from the starting point to the ending point energy decreases by E2, then E2 is equal to the difference of initial energy minus final energy, and therefore is equal to 8 pi r squared t plus 8 pi r squared t, or 16 pi r squared t minus 8 pi times 2 to the power of 2 over 3 times r squared t. Now according to that we can see if E1 is this and E2 is this, then taking these two values of E1 and E2, if we divide E1 and E2, we'll get 24 pi, not 2 pi, 24 pi r squared t divided by 16 pi r squared t minus 8 pi r squared t times 2 to the power of 2 over 3. So you get this expression right here. And now we can see pi r squared t can be divided from everything, and we're left with 24 divided by 16 minus 8 times 2 to the power of 2 over 3. And we can see if we divide everything by 8 again, we'll get on top 3 divided by, this becomes 2 minus 2 to the power of 2 over 3. And therefore the intended answer here is 3 divided by 2 minus 2 to the power of 2 over 3. However, there is a small problem with this question. And the small problem has to do with how bubbles behave. Consider a bubble of radius r. Given a bubble like this, we know that the pressure on the inside is not equal to the pressure on the outside. And we also know if the external pressure here is P0, the internal pressure here will be equal to P0 plus delta P, where for a bubble, delta P is equal to 4T divided by R. Now the problem comes when we apply this principle to the equations that we get in order to find E2. So if we consider E2 is gotten by considering two bubbles, each of radius simple r, being added together and coalesced to create a bigger bubble of radius, let's say, capital R. Now to solve the question initially, what I did was to assume that the pressures inside of each of these three bubbles are all equal, and therefore, when the bubbles coalesce, the volume of the big bubble is equal to the sum of the volumes of the two small bubbles. And with that, I got capital R equals cube root of 2 times simple r. However, that's not exactly correct. It's not exactly correct, and you'll realize why if you consider the pressures inside of these bubbles. So, if you consider pressures inside of these bubbles, the pressure here is equal to P0 plus 4T divided by simple r. However, for the big bubble, it's equal to P0 plus 4T divided by capital R. Now, since capital R is bigger than simple r, we can see the pressure inside these bubbles is not equal to the pressure inside this bubble. And therefore, since the pressures are not equal, we cannot do P1V1 equals P2V2, cancel these two off and say V1 equals V2, but instead have to actually put the actual pressures P1 and P2, substitute, simplify correctly, and get the correct answer for the second radius. So here, if we actually do that, we can see the volume on the left hand side V is equal to double the volume of single sphere, which is 4 over 3 times pi r cubed. And on this side we have V equals 4 over 3 times pi capital R cubed. And according to that, if we apply P1 V1 equals P2 V2, we'll get P0 plus 4T divided by R times the volume of 2 times 4 over 3 times pi r cubed equal to P0 plus 4T divided by capital R times 4 over 3 times pi times capital R cubed. So you can see it is not just P0 on both sides and therefore this volume equals this volume, but rather two little factors here that are slightly different from each other. Now, the only issue here is that in most general cases on Earth, the actual values of 40 divided by simple r and 40 divided by capital R are much smaller than P0. And therefore, it is pretty much like we just put P0 here and P0 here. And therefore, our assumption of this bubbles volume here being equal to 2 times the volume of these small bubbles is pretty much correct. Now, to give you an example of just how small of a difference this makes, let's consider a very small bubble, because the smaller the bubble, the higher the pressure difference will be. So let's consider a small bubble of radius of 0.1 millimeters, just to give a benefit of a doubt. Now T for a soap bubble is approximately equal to 2.5 times 10 to the minus 2 newtons per meter. And according to that, if we take the radius here, which is equal to 1 times 10 to the minus 4 meters, and substitute into the formula of delta P equals 2.5, or rather 40, so 4 times 2.5 times 10 to the minus 2 divided by 10 to the minus 4, we can see we'll get 10 here, so 10 times 10 to the minus 2, and then 10 to the minus 4 turns into 10 to the plus 4 in the numerator. So we have this, which turns into 10 to the minus 2 and this thing cancelling to give us 10 to the plus 2 here, times 10, which is 10 to the plus 3, or 1000 pascals. Now atmospheric pressure P0 is equal to 100,000 pascals. And therefore, even with this super tiny bubble, the error here is only about 1%. So you are right if you argue that this question is wrong and there's an error here where there is actually not the exact value of 2 to the power of 2 or 3 here and 2 here and all of that. You are right. However, practically the errors are so small that we can basically ignore them. So due to that, I'll still stand by the answer of 3 divided by 2 minus 2 to the power of 3 over 2, or rather 2 over 3. However, I will acknowledge that there is a little bit of consideration that's missing in this question, because due to atmospheric pressure, there will still be a small difference of the two pressures, the two bubbles, and therefore we cannot just take volume of the first bubbles added together equals volume of the second bubble. So there's a small error. Now with that, I'm going to end by saying the answer to this question, or intended answer, is answer number 1. Now moving on to question number 47, it says an airplane with two non-identical engines flies over a stationary observer at a low altitude along a horizontal straight path with a constant speed. As the plane flies, the beat frequency heard by the observer from the two engines changes from 8 Hz to 2 Hz. So since the two engines here are non-identical, they would resonate at different frequencies. If the two frequencies here are F1 and F2, then the beat frequency FB is equal to the modulus of the difference of these two, modulus of F1 minus F2. Now according to that, as the plane flies, normally we would hear FB. However, when the plane flies towards the observer, due to the Doppler effect, the frequency FB here gets increased all the way up to 8 Hz. Now after that, when the plane starts flying away from the observer, again due to the Doppler effect, the frequency of B here gets reduced all the way down to 2 Hz. Now given this, they say, assume that the speed at which the plane moves towards and away from the observer is equal to the actual speed of the plane, and given that, using the Doppler effect, find the speed of the plane. Now additionally, they also say, take the speed of sound in air as 330 meters per second. Now considering that, what's happening here is that an observer on the ground is being approached by a plane at a certain speed, let's say Vp, and as the plane moves, it creates a frequency of Fb, which due to Doppler effect is increased all the way up to 8 Hz when the plane moves towards the observer. Now after that, when the plane starts moving away from the observer at Vp, the frequency Fb is now moved down all the way down to 2 Hz. Now for this one, what we will do is to apply the Doppler effect equation. Now the combined Doppler effect equation says F observed divided by V minus V observer equals F source divided by V minus V source, where F observer is the frequency observed by the observer, F source is the frequency of the source that the source actually produces, and here V observer and V source are the velocities observed and source in the direction that the sound travels. And furthermore, V here is the speed of sound in the medium that we are considering. Now in this particular case, since the observer is stationary, V observer is equal to 0. So I can remove that from the formula. Now from that we can see F observed divided by V is equal to F source divided by V minus V source. And we can apply this into the two situations where the plane is traveling toward the observer and away from the observer. Now in the first situation, we have the plane traveling towards the observer and the frequency observed is 8 Hz. So instead of F4, I can put 8 Hz. So we have 8 Hz divided by the speed of sound, which is 330 meters per second, equals, on the other side we have F source, which I don't know, but I know it's equal to FB divided by speed of sound in air of 330 meters per second minus VB. Now, sorry, Vs. Now in this case, Vs is in fact positive because the velocity of the plane Vp is in the direction that the sound travels. So in this case, sound travels towards the observer like this, and therefore I have to take Vp as being positive and substitute it in as Vs. So we have 330 minus Vp. This is equation number 1. Now similarly, if I apply for the second scenario where the plane is passing the observer, the frequency observed there is 2 Hz. So we can write 2 Hz divided by 330 meters per second. Now that's equal to the source frequency of FB divided by, and here we have 330 meters per second minus V source, but here, since the velocity of the plane is going in the opposite direction to the direction that the sound travels, I have to take Vp as being negative. So what we have here is minus negative Vp or plus Vp, and that is equation number 2. Now with equations 1 and 2, I can find the speed of the plane of Vp. So deleting all of this stuff, if I take these two equations only and move them up here, from the first equation I can see, if I rearrange this to get 8 Hz times this thing and 330 times FB, I can see I'll get 8 times 330 minus Vp equals 330 FB. Now similarly, from the other equation, if I do the same rearrangement, on this side I can see I'll get 2 times 330 plus Vp equals 330 FB. So from this we can see if I call this 4 or rather 3 and I call this 4, then from 3 and 4, if I combine the right hand sides, on the left hand side of one of them we have 8 times 330 minus Vp, and on the other side we have 2 times 330 plus Vp. Now simplifying we can see we get 8 times 330 minus 8 Vp equals 2 times 330 plus 2 Vp. Now taking this to this side and this to this side, we can see on one side we can get 8 Vp plus 2 Vp or 10 Vp equals, on the other side we get 8 times 330 minus 2 times 330, and therefore Vp is equal to 6 times 330 divided by 10, which is equal to 6 times 33, which is equal to 180 plus 18 or 198. And therefore, the speed of the plane Vp is equal to 198 meters per second, which is answer number 5. Now moving on to question 48, the question says, a hot copper container with its copper lid of total mass capital M is at a temperature theta 1. Water of mass simple m at temperature theta 2, which is less than theta 1, is poured into the container and then the lid is quickly closed. A student assumes that a fraction x in terms of mass of the water converts into steam and does a calculation to find x. So out of the total mass m, a fraction x, which is like 1/3 or 1/2 or something like that, converts into steam. Now then they finally say, if the student finds that x is greater than 1, which of the following is true? And then they say assume that there is no heat lost to the surroundings. Now here, if m is the total mass of water and x is the fraction that converts into steam, then the amount of water that converts into steam is m times x. Now since x is greater than 1, m times x will be greater than m. Now what this means is that the fraction of water that converts into steam is going to be greater than the actual amount of water that we put into the pot. Now according to that, if we put less than that, which is m, all of the water in m must convert into steam, because the amount of water that we can actually convert into steam is even more than the amount of water that we put in. So 100% of the water converts into steam. So from this we can conclude all of the water becomes steam. Now what this also tells us is that the pot actually had more energy than needed to heat all of the water up to 100 and then boil it. So therefore, when it cools down, it will still be at a temperature higher than 100 Celsius, so that if you put even more water in, that water can also heat up and boil away. So therefore, if the final temperature of the container is like theta 3, then theta 3 must be greater than 100. So we can make these two conclusions from the information given. Now looking at the answer, we can see the first answer says all the water has converted into steam, which is correct, but the second thing says and the final temperature of the system is equal to 100 Celsius. Now if the temperature was equal to 100 Celsius, it means if you add some more water in, it will be less than 100 Celsius, and therefore none of that water would boil. But here, since we know that more water could boil, it cannot be correct. So the answer 1 is wrong, because it says it's equal to 100 Celsius when it should be greater than 100 Celsius. Now moving on to number 2. Number 2 says all the water is converted into steam, which is correct, and the final temperature system is greater than 100 Celsius. That's also correct, which means that answer number 2 is the correct answer. Now if you just look at the others for a second, we can see in number 3 it says all the water has converted into steam, which is correct, but then it says the final temperature system is less than 100. Now again, that cannot be true, because it has to be greater than 100 in order for it to be possible for even more water to evaporate afterward. So 3 is wrong. Now moving on to 4. 4 says some portion of the water has converted into steam, which is not correct, because all of it should convert into steam, and also says the final temperature system is less than 100, which is also not correct. So both of the statements here that added together are both incorrect. Now finally, statement 5 says some portion of the water has converted into steam and the final temperature system is equal to 100. Again, both of these are wrong, since all of it converts into steam and the temperature is greater than 100. So there's the only correct answer here is answer number 2. Now moving on to question number 49, the question says consider the given circuit, and here R2 is greater than R1, which are both much greater than R3. Now given that they ask which of the following inequalities is correct. Now looking at the circuit, the only theory I'm going to apply is Kirchhoff's current law for this point right here. So for this point, we can see the currents going into the point are I1 and I2, and the currents coming out of the junction are I3 only. So therefore, I3 must be equal to I1 plus I2. Now after that, in order to find the answer, it's just going to be trial and error, and looking at the answers, if I consider answer number 4, from answer number 4 we can see we have I3 being greater than R3 times I1 plus I2, which is equal to I3 divided by R3 plus R1. Now if we divide both sides by I3, we can see we'll get 1 being greater than R3 divided by R3 plus R1, which turns into R3 plus R1 being greater than R3. Now since R3 and R1 are both positive, we can see if we subtract R3 from both sides, we get R1 being greater than 0, which is a true statement. And therefore, if it's true, the original inequality here must have also been true. So if you do it like that, you'll get answer number 4 as the correct answer. And here, in order to see whether the other ones are not true, the only real method you can use here is trial and error. Just look at all of them, see if they're true or not all the time, and then you'll see number 4 is definitely true. So with that, we're done with question number 49. Now finally, if we consider question 50, the question says a uniform electric field of intensity E acts in the plus y direction, and a uniform magnetic field of flux density B is directed out of the plane of the page as shown in the figure. So here we can see in the plus y direction, we have an electrical field, and the magnetic field B, indicated by these dots, is acting out of the plane of the page, coming out of the page towards our faces like so. Now given that they then say a particle with mass m and charge plus q is released from rest at the point O. So right here. Now given that they ask us what is the speed of the charged particle at a vertical height y measured from the horizontal like this, and finally they say neglect gravitational forces. Now, while we neglect gravity, there'll still be two other forces that are going to be acting on our particle. They are going to be the force due to the electric field and the force due to the magnetic field. Now, out of these two, since our charge is positive, the force due to the electric field is going to be in the direction of the electrical field. Therefore, the force in this particle will be acting vertically upward like this. I'm going to call this force F sub B. Now, F sub E here is equal to the electrical field intensity of E times the charge of Q. So, Fe equals EQ. Now, similarly, if our particle is traveling at a velocity v like this, then there will also be a magnetic field force F sub B, which will be equal to BQV times the sine of theta, where B is equal to magnetic flux density, Q is the charge, V is the velocity, and sine theta is the sine of the angle theta, which is the angle in between the V vector and the B vector. Now, in this case, since the V vector will only be within this plane of the page and the B vector is perpendicular to the plane of the page, the angle between the V vector and the B vector is always 90 degrees. So, instead of theta here, we can substitute in sine of 90 degrees. Now here, since the sine of 90 is equal to 1, we can see we just get BQV times 1 or simply BQV. And therefore, FB here is equal to BQV. Now, as for the direction of FB, we have to find that based on Fleming's left-hand rule. It says if you take your left hand and you make your fingers like this perpendicular to each other, then your index finger, if you point in the direction of the magnetic field, and your middle finger, if you point that in the direction of the current, then your thumb will point in the direction of the force that's created by that magnetic field. Now, if you do that, you can see by rearranging, since the charge plus Q is traveling in this direction along the V, we can see the current is in this direction, and of course the magnetic field is coming out of the page. After aligning, you can see the magnetic force is going to be in this direction, perpendicular to V and to the right of V like this. So this is the magnetic force FB. Now, according to this, we can see some interesting things. Fe will always be in the upward direction, but Fb will always be perpendicular and to the right of the velocity v. Now, if we consider work done while moving from the origin up to a certain height, let's say y, then we'll see something interesting. Now, if we consider the electrical and magnetic work done separately, for the electrical work done, Wd sub E, that will be equal to the force in the upward direction times the distance in the upward direction. Now, the force in the upward direction is F sub B and the upward direction distance is y. So, therefore, it's equal to F sub E times y, which is equal to EQ times y over EQy. So, the work done by the electric field is EQy. Now, similarly, if we consider the work done by FB, we can see something interesting. Now, as the particle moves, the force FB will always be perpendicular to the direction of motion. Now, according to that, if we consider a small delta time, within that small delta time, as a particle moves, the displacement will be in one direction like this, like S like this. However, the force will be in the perpendicular direction like this. Now, due to that, the part of the force FB that is there in the direction of our motion here is equal to 0. In fact, as our particle moves along any path, the force will always be perpendicular to the direction of motion. And therefore, the work done here will always be equal to 0. The component here is 0, and therefore we have S times 0, which is equal to 0. So, along the entire path, for every single tiny step, the work done is 0, and therefore, when you add everything together, the total work done by FB is equal to 0. Now, according to that, work done by B is equal to 0. Now, adding these together, we can see the total work done on the particle is equal to EQy. Now, in this case, since the particle here is not under gravity, there are no potential energies. And therefore, at this point, the only energy the particle can have can be coming from kinetic energy. Therefore, all of this work done must go into kinetic energy. And therefore, half mv squared must be equal to EQY. Now considering that, we can see if we rearrange, we get V squared equals 2 times EQY divided by M, and therefore V equals square root of 2EQY divided by M. Now here, since we took the square and square rooted, what we have here is not actually velocity but rather speed, and therefore the speed of the particle at a height y above the x-axis like this is going to be equal to the square root of 2EQY divided by M. So therefore the answer here out of all of these is answer number 3, square root of 2QEY, or 2EQ, same thing, divided by M. So the answer here finally is answer number 3. And with that, we are done with the questions from 41 up to 50. So I hope you enjoyed. If you have any feedback or questions, post them in the comments down below. Thank you for watching, and goodbye.